Hello everyone, my name is Deepak Singh and in this video I will take you through my project titled Privacy Preserving Face Matching in Digital Space. The core idea that is there is to match faces without ever storing or using the original image, a crucial step which is needed in building privacy-based machine learning systems. So let's begin with the motivation. In today's world where surveillance and biometric authentications are used everywhere, there is a growing concern about data privacy. We have heard about how the biometric data is getting leaked or some other forms of data is getting leaked. So we want to keep that thing in mind. So talking about the raw facial images, if they get leaked or misused, they can't be changed like passwords because they are fixed or permanent according to person they are deeply personal to. So the question I wanted to explore was that it can we still perform reliable face recognition while keeping user data private. This project addresses that by using the PCA, that is Principal Component Analysis, the thing that I studied in this course, to use face data into compressed anonymized representation. By doing so, what we will achieve that we will avoid storing or transmitting wrong images while still being able to match identities. So let us move to the what is the connection to past and the current work which is doing in the machine learning. Traditionally, what used to happen that face recognition has relied heavily on deep learning models like FaceNet or DeepFace. What but these models deliver higher accuracy, but they come with a cost. They often require large datasets of raw faces, creating major privacy concerns. Interestingly, PCA was one of the earliest tools used for face recognition, famously in the name of Eigenfaces method. So we will go through this method. So this work revisits PCA not to beat the deep learning on accuracy front. We know that deep learning models will be better on accuracy front, but they are most focused for privacy first framework. So let me take you through the code which I have used for this. So we start by importing all the necessary libraries that we use like NumPy, Matplotlib for plotting images and graphs, and tools from scikit-learn, including PCA and a Livid Faces dataset. So in the first part, we have done this. So I have initially run all the code blocks to save time on that front. So now talking about data set. So we have considered the image of 40 individuals and that ID is stored in this y equal to faces.target, which contain ID corresponding to the each face. And talking about the image, so if each image is a gray scale image and which is 64 cross 64 pixels, and there are about 400 gray images of 40 individuals. In X, we are storing the flattened image, and each image is a 2D, and this is that thing. Now, in next part of the code, we have defined the PCA and the KNN model. KNN model is to basically evaluate the KNN classifier. So this is the part in which we have defined the PCA function, KNN function. So in next part, what we have done, then in next part, we then analyze the explained variance versus number of components thing. In x-axis, we have number of components. In y-axis, we have cumulative explained variance. Basically, we are showing that if we retain, let us suppose, 100 number of components, with how much variance we are capturing. So if you can see that if there are 50 components, then we are capturing close to 90% variance. If there are 100 components, we are capturing more than 90%. Similarly, if we increase our components, the more amount of variance we will be able to capture. So what we will try to achieve that we will try to find that number of components in which we can achieve enough number of variants so that we can do the face reconstruction. So here what we have done. So in this part of the code, basically what I have done that I have let us suppose that I this is the original face and this is the face that is suppose that we have reconstructed with just taking 50 principal components. Let us suppose that if I reduce this component, so let us say 10. So you can say that the face which is reconstructed is less accurate or less close to original. If I increase, let us suppose that my number of components is 140. So you can see that original reconstructed face is almost similar because we are able to capture more amount of variance. So this is the case that if we increase number of components that we will be able to capture more variance and more reconstructed face will be closer to original face. Now, what we have done that now we have evaluate now with the number of pixel components we will try to get a training classical accuracy. So what we have done that we have split our data into 75% training and 25% testing, ensuring that so that a training recognition logic is evaluated fairly. So in this, what we are doing that in x-axis we have considered number of components and y-axis we have taken classical classification accuracy. So let us suppose that if we use 40% of components, then how much classification is getting correctly identified? Basically, what we are doing is let us suppose that we have taken reduced number of components, then we have to match this face with the original face. So this accuracy is telling that number that let us suppose that we have 40 number of components. So with how much percent we are able to identify that whether this phase is correct or not. So this code block is here and this we have plotted. Now in this part of the code, what we have used that we have used cosine similarity to compare faces in the compressed space. If two vectors are close enough, then we say that we treat them as a match. Let us suppose that here is a test index. Test index basically corresponds to different faces of a person. Here we have taken into consideration only 50 components. Let us suppose that if, if, if different test index is there, which means that we are taking the IDs of different persons and we are using the face corresponding to that ID. So let us suppose that we have reduced faces into using PCA. This is the face which we are storing, and this is the original face which we are not storing. Let us suppose that this is the face uh, we have we have in PCA space. We have to find the original face corresponding to this test face. So let us suppose this is one face. So here we can see that this is the face in reduced number of PCA components, and this is the original face. So we can identify the original face with the help of match face. So this is the face which we are storing. We are not storing raw images, and this is the test face. So you can see that they both are similar, which means they are correspond to same person. Suppose that we take different test index. So yeah, this is the face in reduced number of components, and this is the original face. So we are able to recognize the original person using the compressed faces. Now, after this, this is all this is all about PCA. Now we have also used the autoencoder. Autoencoder is also used is a deep neural network based thing that is used for also face recognition. So here we have imported necessary libraries which is needed for face recognition. After this, we have trained an autoencoder for face feature extraction. And here the thing that we did using PCM that we calculated the classification accuracy. The same thing we did using autoencoder. So accuracy comes about 0.44%. This accuracy will highly depend upon the number of hidden layers we are taking, what is the activation function we are using. So that thing will definitely determine our accuracy. Now, in next step, we have compared results of PCM autoencoder. So this is the original face, and this is the face reconstructed with the help of PCA, and this is the face help reconstructed with the help of autoencoder. Similarly, this is the face, these are the five test cases we have considered. And in next case, what we have plotted a difference in how much there is difference in the face recognition of both PC and autoencoder. That is plotted here. So that is the thing we have done. So talking about the PCA thing, so if I talk about the PCA versus autoencoder, so what I have learned or what I have while I was studying about autoencoder, I found that the autoencoder results will be better, but I don't know. I was not able to train the hidden layer. I'm not able to increase the hidden. My output was not getting better even if I was increasing hidden layers. But on internet, it was mentioned that the autoencoder result is typically better. So first of all, talking about the PCA, that PCA is first of all very simple, but it is quite outdated. But also, I was surprised by that how robust and strong results by just considering the 50 PCA components. For example, here if you see that with 50, just which is close to your 50 principal components, we are somewhat we would be able to identify what will be the original phase would be there. So for improvements, I also explored this autoencoder reconstruction method, which is non-linear because there's little involved here. So so now talking about uh, talking about the reflections, that what surprised me that this project helped me understand that how we can rethink face recognition and privacy respecting way. It was refreshing shift from blindly chasing accuracy to thinking about what data we use and how we use it. So that's all from my end. So one thing I would like to mention that while PCA helps anonymize data to a degree, but with the help of PCA, what we can achieve that our accuracy may be less. But PCA, we could think from the accuracy point of view that with less number of multiple components, instead of storing original space, we can store compressed space. Even if that data get leaked, it will not be a major risk. So these are all the references that I have used. So yeah, that's all from my side.